Herkese merhabalar. Nano Open Webinarı'na hoş geldiniz. Bugün çok değerli bir konuğu ağırlıyoruz. Gebze Teknik Üniversitesi'nden Doçent Doktor Sayın Serkan Büyükköse konuğumuz. Kendisi bize metal oksit tabanlı kimyasal dirençli ve kütle duyarlı gaz sensörleri hakkında bilgiler verecek. Serkan Hoca aynı zamanda bizim sunumun ilk 1004'ü olan NanoSys platformunda da düşük derişimlerdeki özel ajanların belirlenmesi için özgün malzemelerin ve fonksiyonel yüzeylerin geliştirmesi projesinde yer alıyor. Serkan Hocam hoş geldiniz.
Merhaba, hoş bulduk.
Sözümü mikrofonu kendisine devretmeden önce hakkında kısa bilgi aktarmak istiyorum. Doçent Doktor Serkan Büyükköse yüksek lisansını 2009 yılında İzmir Yüksek Teknoloji Enstitüsü Fizik bölümünde tamamladı. Yüksek lisans çalışması sırasında metalik ince filmlerin taramalı uç mikroskobu yöntemiyle elektriksel özelliklerinin modifiye edilmesi üzerine çalıştı. 2014 yılında Hollanda'da bulunan Twente Üniversitesi Nanoelektronik grubunda doktora çalışmasını tamamladı. Doktora sırasında yüksek frekanslı yüzey akustik dalgaların üretilmesi, karakterizasyonu ve düşük boyutlu sistemlerde akustoelektrik yük taşınımı üzerine çalışmalarda bulundu. Doktorasının ardından Almanya'da bulunan Poldrude Katı Hal Elektroniği Enstitüsü'nde yarı iletken spektroskopisi bölümünde doktora sonrası araştırmacı olarak görev aldı. Büyükköse 2016 yılından bu yana Gebze Teknik Üniversitesi Fizik Bölümünde öğretim üyesi olarak çalışmaktadır. Son yıllarda araştırma konusu özellikle metal oksit algılayıcı katmana sahip kimyasal dirençli ve kütle duyarlı gaz sensörlerinin geliştirmesi üzerine odaklanmıştır. Serkan Hocam tekrar hoş geldiniz. Ben ekran paylaşımını size devrediyorum.
Tabii. Şu an ekran paylaşımı görülüyor diye tahmin.
Görüyoruz hocam. Evet.
Ee, Çok teşekkür ederim tanıtım için. Tabii ben sunumumu İngilizce hazırlamıştım, İngilizce yapacağım diye düşünerek. O yüzden izninizle İngilizce devam edeceğim. Um, okay, so thank you very much for the introduction. I think it's a privilege to give a speech here, and it's my pleasure actually. And today I'll give a general overview what we are doing in our research lab. And actually, it will not be focused on a complete work from starting to end, but as I said, it will be a general overview. Um, and the title of the speech is Metal Oxide-Based Chemiresistive and Mass-Sensitive Gas Sensors. But to be honest, to give a very long title is not the good thing for me. But when the topic is the sensors, you have to limit it by using some words, special words. Therefore, it's a bit longer than I think. Let me show you the outline of the talk. Um, First, I would like to define what is a sensor, what a sensor is, and then I will talk about the types of sensors and working principles of the chemiresistive and mass sensitive sensors. Then I will talk about how we fabricate these sensors, both the platforms and sensing materials, and then I talk about the measurement setups for different kind of sensors, and finally I'll give very limited the examples from our recent works. Um, okay, if you look at this definition, which says the sensor is a device, um, sensor is a device which detects. Okay, can you see the laser pointer here? Oh, okay,
Hocam, we can't see the laser sign.
okay, it crashed, as I said before. Uh,
Murphy joined the meeting. Uh, Maybe you can stop the share and again share your screen.
okay, PowerPoint crashed. Let me restart it, and I'll not use the laser pointer again. Okay. Um, Let me share again. Okay.
Yes, we see it now.
Okay. If you look at the textbook definition of a sensor, it's a device that detects the feature quantity of a measurement object and converts this quantity into readable signal. Okay. It seems that it has two main functions. One is the detection or recognition, and the other one conversion or transduction. And then a question comes into mind that why don't we call then this device as detector? Because anyway, we know there are some devices called as detectors and some devices called as sensors. The term actually sensors and detectors are often used interchangeably, but they have distinct meanings in many contexts, especially in scientific applications. Here you see the most simplified difference actually. When we talk about sensors, the sensor measures a physical quantity and converts it into a signal to be read or processed later on. And mostly it focuses on continuous measurement or monitoring. But for the detector, it's a bit different. It identifies the presence or absence of a specific event, specific substance or condition. And it's not focusing on the continuous measurement, but it's just the focusing on recognition. And also when we talk about the sensor, we have to indicate that the sensor consists of two components, which are sensing material, which is responsible for detection, and the other one is transducer, which is responsible for conversion or transduction. So as long as you have both sensing material and transducer, you can talk about a sensor. Otherwise, you cannot talk about a complete sensor. There are a huge number of sensor types used up to now, and if you look at the literature, you will see different classifications, but there is no really the generally accepted classification rule. Therefore, I'll not give it this messy information, but in our case, for our devices, we can make a classification according to sensing mechanism. So according to sensing mechanism, we can classify our sensors as chemiresistive sensors and mass sensitive sensors, because this classification can be done according to what these devices are trying to sense, what these devices are, what kind of transduction technology they are using, or what kind of sensing material they are using. But in our case, if we classify our sensors according to working principle, we can say chemiresistive sensors and mass sensitive sensors. Let me first explain the mechanism of metal oxide semiconducting gas sensors. So here what you see is an N-type material, metal oxide, semiconducting metal oxide, and this the semiconducting metal oxide absorbs some oxygen molecules which trap the electrons as oxygen ions on the material surface. Thus, an electron depletion layer is formed on the N-type material, whereas the hole accumulation layer also formed on the P-type material. Okay. These electron depletion layer and hole accumulation layers are called as phase charge region. Okay. On the exposure of reducing gases, these trapped electrons release back to surface, and this one changes the conductivity of the conductivity of the surface. So, releasing back the electrons increases the conductivity or changes the resistivity, and you can read this as a sensor signal. It's similar in also the P-type materials, but in case of oxidizing gases, the electrons further trapped to the oxidizing gases, and the electron depletion layer increases, which gives further decrease in conductivity. And this altering of conductivity can be read as the sensor response for the chemiresistive sensors. If you look at the mechanism of the mass sensitive sensors, which here I'm talking about the QCM, which is quartz crystal microbalance. It is actually a piezoelectric material sandwiched between two electrodes. And if you apply time varying voltage to these electrodes, you can vibrate the QCM with its resonance frequency. And actually this QCM technology is very well established, and it's already commercially used for most the thickness monitoring. I'm sure you are all familiar with the thickness monitoring in vacuum chambers in laboratory, and you see there's a formula which gives the frequency shift according to the mass load on top of the surface. Okay, if you have a sensitive layer on top of one of the electrodes, and if some gas molecules are absorbed on it, then this appears as mass loading, which is indicated here delta M, and it appears as a shift of frequency in resonance. So here, by using this the formula, you can easily calculate the thickness of the material, or you can just get the sensor response by measuring the shift in resonance frequency. Another mass sensitive technology for the sensors are the surface acoustic waves. Surface acoustic waves exploits the inverse piezoelectric effect. In case the piezoelectric material, you apply some strain, and you induce a polarization or electric field in the material. So actually the reverse is also possible. I mean, if you apply electric field, you get also physical displacement on in the material. So it's called as inverse piezoelectric effect. Now suppose that you have a comb-shaped electrodes on top of a piezoelectric substrate, and if you apply RF time varying signal or RF signal, you can create some displacement on the surface. And at a certain frequency, for this displacement, a constructive interference occurs, and surface waves are released and propagate on the surface. And the frequency of this propagation depends on the pitch size of the electrodes here. As you see, this one is the relationship. So here, narrower fingers and narrower spacing between the fingers means that higher frequency. If you look at more details of the acoustic waves, generally they are, of course, the mechanical waves, which with longitudinal and transverse components. But it should be noted that in case of piezoelectric substrate, it's not only a mechanical wave, because in case of piezoelectric substrate, there is also the electric potential wave accompanying the mechanical waves. It's sometimes important for the sensitive applications, but in our case, dominant mechanism is the mechanical interaction. So I'm not talking about this electrical wave, but it's not only mechanical wave in case of the piezoelectricity. And if you look at how the materials or atoms or molecules moves under the influence of the surface wave, it follows an elliptical motion, and these waves propagate with the sound velocity on the surface. Sound velocity means that they have a few kilometers per second, 3 or 4 kilometers per second, and which is much lower than the electromagnetic waves, which makes this source very useful for different applications like the filters or signal processing and so on and so forth. Okay, then now the question why the waves are useful for sensing applications. The answer is not given yet. For the answer, let's look at the depth and strain profile, strain and or the acoustic field, acoustic energy profile of the surface. So here, what you see is the strain energy or acoustic field versus depth profile. Here, as you see, most of the acoustic energy is restricted to very close vicinity of the surface. So it disappears in almost in one wavelength, it disappears. So if you, for example, if you suppose that the wavelength of the wavelength of the acoustic wave is, let's say, 2 micrometer, then in 2 micrometer depth, all the energy is constricted. So means that if this energy is restricted to the surface, it's very sensitive to any perturbation on the surface. So what kind of perturbations I'm talking about? So here you see this perturbation might be temperature, might be electric field, might be the conductivity, mass loading, the pressure, and some other physical changes on the surface. So any kind of perturbation can be seen as the shift. It can be seen as the change in velocity of the acoustic field, acoustic wave, or shift in frequency. So in case of surface acoustic waves, then the measurement can be done by using the configuration. Here again we have the piezoelectric substrate and one generating interdigitated electrodes and receiving interdigitated electrodes, and in between, which is called as acoustic pad, actually, we have a sensing material. In case of gas molecules absorbed here, we see a change, a shift in resonance frequency. So this can be measured by using the vector network analyzer. Of course, it's not the only way to make the measurements, but in our case, we use for now the vector network analyzer for the measurements. Okay, let's now talk about some applications of gas sensing. There are wide range of applications for the gas sensing, from food safety to environmental monitoring, from the smart home to the medical health, also the aerospace, and so on and so forth. But among these application areas, our motivation is mostly medical health, environmental monitoring, and security. Today, I'll present some works motivated for the medical health only. Actually, at the first glance, it's difficult to make a connection between medical health and gas sensing, but there's a very close relationship actually. If you look at this figure, you see for the almost 1% of the human breath is formed by volatile organic compounds. Okay, so VOCs. So these VOCs, in some cases, for example, acetone or carbon monoxide or methane, exist in ppm level, which is particle per million, and some others like ethanol, propanol, ammonia are in ppb level. So ppb means particle per billion. So, okay, it's fine. In human breath, we have some volatile organic compounds, and then why we should measure them? Okay, we should measure them, or it would be nice if we measure them, because all this or most of these volatile organic compounds are biomarkers for some certain disease. For example, the acetone is the biomarker for diabetes. Ammonia is the biomarker for kidney diseases. For example, ethane is schizophrenia, and nitric oxide is for the asthma, and so on and so forth. So you see some others, hydrogen cyanide and the carbon monoxide. So here in this graph, you see the concentration of these volatile organic compounds for healthy and unhealthy person. So you see these are mostly in the sub ppb sub ppm level. So this means that it's quite, for, at least for the health monitoring, it's important to detect the gases in sub ppm level, a ppm or ppb level. Okay. Now let's look at how we fabricate our sensors. As I said, sensors are composed of the both transducers and the sensing material. So now I'm talking about the fabrication of transducers. For the fabrication of transducers, we use microfabrication methods. Actually, for the details, you can check the reference here. And basically, we use 3 lithography steps, and at the end, we get a 6 mm by 6 mm chips. It's actually silicon substrate with silicon oxide on top and silicon nitride between platinum heater and gold electrodes for chemical and the electrical isolation here. So this transducer is also called as sensor platform, by the way. So sometimes I call it the transducer, sometimes I call it the platform. Please don't be confused it, because sensor platform means also the transducer. Okay. So this one is for the chemiresistive the platforms, and for the SAW platform we use a bit more simple the fabrication process due to a single step lithography. In this process, a comb-shaped interdistinct electrodes are deposited on top of a piezoelectric substrate like the quartz or lithium niobide, and at the end we get something like this. You see here a 4-inch wafer, and you see some different some different designs for the source of space. Here in between, this region is actually the active region. So previously I called it as acoustic pads. So this, if you put sensitive layer on this acoustic pad, you can get a sensor actually. Okay, these are the fabrication processes for the transducers, and now let me show you the formation of sensing materials. So for the sensing material, we mostly use hydrothermal method, and also for the ultra thin film formation we use atomic layer deposition method, or sometimes we use the sputtering method. So actually here the hydrothermal method is very useful for to get the nanostructures, because by using hydrothermal method we can get nanorods, nanoflakes, nanobricks. Here the important point is to get higher ratio for the surface volume. I mean, if you increase the surface volume ratio, you can increase the interaction between the analytic gases and the surface. So therefore, getting the nanostructure is really desired for the sensor applications. So hydrothermal method is one of the most used method in our lab actually. But sometimes we use some combination to get some heterostructures or shell structures. Okay, let me also talk about the measurement setup for the chemiresistive sensors. And here you see a complete setup. You see the complete schematics of our measurement setup. There's a gas chamber in which we mount, this was the gas chamber in which we mount our sensor, and you see the real shape here. It's approximately it has approximately 1 liter volume, and low concentration gases are generated by special tool. This is gas generator here, and it's sent to the sample with carrying gases. Mostly in our case, it's dry air. All the flows are controlled by the flow controllers, and by using fit-through connections to the chamber, we get the sensor signals by means of the electrometer, and we can also control the temperature in case we don't have a self-heating structure on the sensors. Here you see another setup for the source sensor measurements. Again, we have a gas chamber which has much smaller volume. Here you see it when compared to previous one with SMI connections due to RF signal. So the frequency shift of the sensor is detected by the vector network analyzer, and all the flows are controlled again with the mass flow controllers here. So here, let me show you a work, one of our works. Here, what you see is an alumina substrate with nanoflakes on top. Here, the interdigitated electrodes grown by shadow mask directly evaporating the gold structures here. And here you see the sensor, the formulation for the sensor response. Here, the sensor response for reducing gases is defined by the equation 1, and for the oxidizing gases, it's defined by the equation 2. Here, the Ig is the saturated current after the sensor is exposed to gas, and I0 is the baseline current. So there are some different calculations for the sensor response, but in our case, we directly measure the current and we calculate the sensor responses by using this formulation. But as I said, in literature, there are some different kind of calculation methods as well. They sometimes give the percentage, or they sometimes just measure the resistivity or the resistance. And okay. So now let's look at the shape of nanoflakes on the surface, I mean the morphology of the surface. So here what you see is the some images of hydrothermally synthesized nanoflakes. Here, as I said previously, higher surface volume ratio is an advantage for the higher sensitivity due to increased number of interaction on the surface. Therefore, this kind of morphology is always desired for sensing materials. So you see here the results for the different synthesis conditions, mostly with the time, but with changing time and the temperature. And if you look at the measurement results, with this structure, we were able to measure the ammonia even at 1 ppm level. Here you see the response of our sensor from 80 ppm to 1 ppm against ammonia, and even at 1 ppm we see very clear signal actually. So also on the right hand side you can see also the compression with interference gases. So here the interference gases are chosen as the acetone, ethanol, ICN, and NO2. They are all also the gases exist in excellent breaths, human breath. So it seems that tungsten oxide nanoflakes are quite selective against ammonia at low concentrations. Here it seems like interesting for NO2. Here NO2 is giving a response in the reverse direction because it's an oxidizing gas. All the others are reducing gases. So oxidizing gas increases the conductivity, increases the resistivity further. Actually, you see some other results here. Some temperature dependent the measurement here. Okay, most of the time for the metal oxide, semiconductor metal oxide structures, it's quite difficult to get a response at room temperature. It's always you always have to heat up the sensor because you need some activation energy for the reactions. So the best results in our case are obtained for the 200 degree. Actually, even for 100 degree, we have some response, but it's very, very small. And if you look at the mechanism here on the right hand side, you see a consecutive the nanoflakes. You see for the nanoflakes, as I mentioned previously, there's a depletion layer formation due to oxygen absorption on the surface. By the way, this oxygen absorption or the kind of oxygen ions depends on the temperature. So they might be the molecular oxygen or atomic oxygen. It depends on the temperature. So with the absorption of this oxygen, electrons are trapped, and there is an increased space charge region here. And after exposure to reducing gases, some electrons are released back, and this space charge region decreases, which increases or it decreases the potential barrier here, and it increases the conductivity. So it appears as the sensor signal in our case. Okay, let me show you some other results from the SAW-based sensors. In our SAW-based sensor, we have a quartz substrate and one interdigitate electrode here, generating IDT and receiving IDT, let's call it. And in between, we have sensing material. In our case, the sensing material is zinc oxide nanostructures. They are nanorods, again, obtained by using the hydrothermal method. So, if you, okay, here you see the sensor response of SAW against the acetone. Here, actually, its range, the concentration range is from 7.5 ppm to 750 ppb, actually. So it's in the range of in the range of concentration exists in human breaths. So actually the data looks a bit noisy, but it's due to the insufficient precision of the measurement tool, actually. So now we have the much better tools in our laboratory, and but as I said, this noise comes from not the sensor itself, but from the measurement tool, actually. But as you see, on the left hand side, you see the very small concentrations from 7 ppm to 0.7 ppm. But on the right hand side, the ppm level is a few hundred. So it appears as a kilohertz shift in resonance frequency. You see here the shift is approximately 2.5 kilohertz, but for the small concentrations, it's a few tens of hertz. So this one is just for the acetone measurements. Actually, oops. Okay, these are the sensor. These are our sensor research fields and our activities. Actually, I'm not going into much more details of the measurements. By the way, these last data are not published yet, and we have much more interesting results still waiting for the comments. Still, we have to make some deductions about the interaction between the surface and the sensor platform. And here, I'd like to thank all of you for listening, and I'd like to thank our team from Gebze Teknik Üniversitesi, Professor Dr. Zafer Ziya Öztürk, Dr. Onur Alev, and Dr. Alp Kılıç. I call it almost doctor because he already defended PhD work, but it's still waiting for the paperwork to be called as doctor. And also collaborators from our nanosys platform, Doçent Dr. Mustafa Kemal Beyazıt and Yılmaz Şimşek, and also Professor İzzet Kale from University of Westminster and Volkan Turgul. Actually, I would like to indicate that we are very open for new collaborations, especially for the new material synthesis or data analysis. Um, and also, I would like to thank to the Nanosys platform again, because recently we get a new the project funded by the TÜBİTAK, and it's actually arising from a collaboration in collaboration with Mustafa Kemal Beyazıt Hoca in Nanosys platform. So maybe it's also better to indicate that there are some scholarship opportunities, and the people who are interested can contact with me or Mustafa Kemal Hoca for the further details. So, okay, so thank you very much for listening.
Serkan Hocam, thank you very much for your presentation. Now, Q&A session is open. You can ask your question directly to Serkan Hoca, or you can write it in chat box.
Hey, may I ask some questions?
Yes.
Can you
Yes,
listen?
you can ask. Yes, we can hear you.
Okay, hello. Hello, Mr. Serkan. My name is Serhat. I'm also a physicist from Marmara University. I have some questions. But first of all, I want to thank you and congratulate for this stunning slides and presentation. The first one that I want to ask is, what is or are the other techniques to measure the gas frequency? It was in the slides for the measurement techniques, I think. If you just record this question, I will ask step by step, or if you just want to answer, I can wait. Which would you like to answer?
In our case, we are as I said, in our case, we are using the vector network analyzer, and
you said that we were using the vector analysis, but and you just said that and contribute there are so other techniques,
yeah.
But you did not expand it. I just wonder what are the other techniques.
Okay, one of the other techniques is by using the frequency generator. You can directly apply the resonance frequency to the generating IDT, and from the receiving IDT you can use the frequency counter. That's the another method, for example. Or you can design the RF signal for driving the system, and you can just measure the change in phase, not directly the higher frequencies, because we are dealing with the approximately 150 megahertz frequency, so it's difficult to design or drive the system with this high frequency. So sometimes it's much practical to just measure the shift in the phase by some mixers, for example. But it's actually the multidisciplinary work, so it's most electronic engineering process actually.
Okay, for the gas cell, do you get vacuum the chamber before the measurement, or you just sweep the gas into the chamber?
No, we just sweep the gas. We actually, as I said, we use carrying gas as dry air. First, actually, we send the dry air to the chamber for a few hours before the measurement to clean the surface, to get rid of at least the relative humidity, because the most important or the obstacle actually for the gas the sensor applications is getting rid of the relative humidity. So we don't use any vacuum, we don't use any pumping process. We just send the carrying gas into the chamber before we send the gas we would like to make.
But can it be a source for the noise? Because my next question was about like that. What were the source of the noise in the measurements of the signals for the, I think, tungsten trioxide nanoflakes, right? You have used this material, tungsten trioxide nanoflakes, yes. And you have also mentioned that we have some noises in the analysis. So maybe this vacuum or not to get a vacuum before the measurements can be a noise problem? Or what are the sources, or what is the source for this noise on the signals?
Actually, for the tungsten oxide nanoflex, I don't think we have the noise issue.
You have just, I mean, and the previous slides, if you just open it, you just come back. Yes, you passed it. Come back, please. One slide only, maybe. Yes, here. You take, the baseline, not baseline. This is, I mean, the section.
Okay.
And we have so many noises right here.
Let me make it clear. This is my mistake. It's not tungsten oxide nanoflex sensor. It's zinc oxide nanorods. Sorry.
Okay.
It's not tungsten oxide. So sorry. It's just
okay. The problem doesn't change, because I mean the question also can reveal the noise problem. Maybe if you would like to say, because here we have so many noises. And I just wonder that what are these sources for these noises? Maybe can it be the chamber problem, not getting the vacuum before the measurements, or the other?
It's not related with the. It's not. The main source of noise here is the precision of the vector network analyzer. Its precision is 7 pp. So. It means that for the 1 megahertz frequency, it gives 7 hertz on precision.
Did you think about it? I mean, in the way of 2 probe or 4 probe, because your transducers are with 2 probes, right?
Yes.
The general classic type is 2 probes. Maybe you can think while printing or for this microfabrication techniques for the lithography process, maybe you can think the 4 probe techniques. Because when you use the 4 probe, the resistance, I mean the self-resistance of the system can be elucidated, can be deleted, can be removed. You know it as a physicist. So maybe you can think about it for your further works or study.
Okay, I see your suggestion, but it's bad for the chemiresistive sensors. For chemiresistive sensors, we have already very high resistance, so we don't really need the 4 probe measurements. So 2 probe measurement is enough for the chemiresistive. But here,
it's obviously seen. It's a very, very successful study. I mean, I'm very happy to see it. It's good. Thank you very much for your contribution and your presentation again.
I thank you very much.
I just much appreciated within this presentation. Okay, thank you.
Any question?
Question from my side, actually. Serkan Hocam, thanks a lot for nice presentation. I'm interested in the mechanism of, the ammonia sensing. So in that mechanism, there is water elimination somewhere on right-hand side, N2 plus water plus electron. So normally we consider, while doing these type of measurements, what the humidity level is in the chamber. So do you think, that water elimination is causing any relative humidity change in the chamber and concurrently affecting the measurements? Or just, that water is being purged by the gas coming into the chamber?
Actually, I don't have a distinct answer for it. It might be purged by the carrying gas, because anyway, it seems that after the interaction here, you get you're right, you get some water here. And some electrons are released, but we don't know if this water is absorbed on the surface. But if we think that it's at temperature of 200, it's not so possible to keep this water here. Probably it's slipping with the carrying gas, because the surface has very high temperature. So it's just an estimation, but I don't have any proof for it.
Thanks a lot.
Any question? And dear Serkan Hocam, thank you for your great talk, for your time, for your effort. Dear participant, thank you again for your participation. See you next Nano Open Webinar.
Ben de çok teşekkür ediyorum herkese. Yaptıklarımızın daha detayını merak eden arkadaşlarımız varsa her zaman collaboration açığız dediğim gibi. Özellikle Serhat Hocam'ın soruları için çok teşekkür ederim. Çok ilgilendi sağ olsun. Daha detaylı sorular sormak isterseniz hocam her zaman buradayız.
Çok teşekkür ederim hocam. Sağ olun. Ben de çok mutlu oldum sizi tanımaktan dolayı. Eminim ilerleyen günlerde tanışmak için sizle iletişime geçeceğim.
Umarım.
Tekrar çok teşekkürler.
Serkan Hocam teşekkürler. Ağzınıza sağlık.
Hoşça kalın.
Hoşça kalın.